Okay, so you probably noticed that I've uploaded the exam for grades. The last homework set, reading smart module for chapter 14, the last chapter we are going to cover in this and next week. And I think that's about everything we are going to have in the final exam. So I want to briefly mention something about the exam 4. I see a big improvement in the exam 4. For the first time, we have a perfect exam 100. Somebody want to say something over there? And the average is 72. We still have a few students who are struggling in the exam 4, but the majority of our students are improving in the exam 4. I hope to see the same trend in this final exam. And final exam will be in roughly 2 weeks. So that's all I have for the exam 4. I shall send you the statistics of the point distribution of the exam 4. Okay. So as for the last chapter, I shared all these slides. I think those would be the slides we try to cover in roughly 3 lectures. So we'll see what's the difference between the chapter 14 and previous discussions. So if we recall, previously we were talking about
Professor.
Yeah.
Someone did have a question. Does our grade include the bonus points, or is that the actual score on the test?
No, that's the actual score. Include the bonus point or no, that's the actual score. I don't know why, Christine, you would ask for the bonus points. Well, I mentioned to two students. Two students deserve some bonus point because they noticed something from the exam and they helped me to correct the exam. I think I need to identify the other student. I do have one student I need to email to the class and I identify who that student was during the exam to help me on the exam correction. But other than that, I think no bonus point to the class.
Wasn't there like for the people that show up to class like a few weeks ago?
Well, that's to the end. When I assign the final letter grade, I will.
Oh, okay.
I will consider that sort of surprising bonus, and then remember we had a resubmission for exam 1, right? Not everybody did that, but I'll try to look for those copies and consider that factor when I assign the final letter grade.
Thank you.
Yep. So anyway, I'll email the class for some small stuff over the exam 4. Okay. So now coming back to the slides, we were talking about our favorite equation. And I hope you guys still recall that favorite equation, which is coming out of the system setup. I have a black box or a reactor container, a separation tower. I'm going to have the inlet, which is a mixture. Zi, do we still know how to describe Zi? The overall composition of component I of the mixture. Zi is Xi of the liquid plus Yi of the vapor, right? So from there, we were talking about the bubble pressure, doped pressure calculation, so on. So over there, we are going to have, say, 1 and 2 as the mixture. And then we are going to manipulate. This is at T naught and P naught. And then in this separation tower, that would be T and P. So very likely we are going to further split the vapor and liquid. So in the end, we are going to have the final vapor and final liquid. And we want to see what would be the y I prime. Prime means it's actually changing from the inlet. For the liquid, we want to see the xi prime. Right. So that is the general problem setup for the previous discussion, especially for the vapor liquid equilibrium. So over there, I hope you still recall that the most general equations would be the criteria for vapor liquid equilibrium, where we have to satisfy temperature, say in the liquid would be the same as the temperature of the vapor. The pressure of the liquid will be the same as the pressure in the vapor. So for the first two equations, we typically think that those equations we are able to manipulate very easily. So we don't have to worry too much. No need to worry too much about that. No need to worry over here. Okay. So that is a understanding that we are able to control temperature and pressure very easily. Of course, measure them. So the last critical equation we have to satisfy is the fugacity. For the component in the liquid phase shall be, excuse me, exactly as the fugacity in the vapor phase. And if we want to make it more like reflecting the mixture, then we try to have the head, right? And of course, this is exactly the same as mu I in the liquid if we are using chemical potential instead of using uh, fugacity, then that two equations are identical. Okay. So really the calculation was about the last equation of fugacity. So over there, if you recall, we were having the discussion. We try to divide these systems into three different groups. One is low pressure. If this is low pressure and we have ideal solution, that means we are going to use the Raoult's law for both vapor and liquid, right? Where we are going to have this vapor component would be simply YIP, right? And then the liquid component would be, if this is ideal solution, then we are going to have the XI, FI, Q, right? And if this is a Raoult's law, then this is XI, PI set. So that is the first case. The second case is it's still relatively low pressure, meaning we are still using ideal gas. However, the liquid is having complicated intermolar interactions, so we are going to have the real liquid. Then the third case is it's any pressure. And then we are going to have the real liquid. So moving from group 1 to group 2 and group 3, eventually we are moving to the equation using the fugacity and activity coefficient. So we are going to have this that would be the general equation we are using for all those calculations, right? And if during the process, if you have to manipulate the temperature, then if you try to manipulate the energy, then you probably need to calculate the change of enthalpy of the system. so that you know what would be the temperature effect for the general calculation. And then, of course, over there, you are going to express whether it's fugacity coefficient or activity coefficient. Sometimes we try to calculate this as a function of temperature. And then we plug the equation back to the general equation to finish the calculation. Okay. So this is a very typical VLE. The main point here is that we try to redistribute molecular with phase change. The other method is we are also able to redistribute the molecules by removing them out of the system, or by reactions and create more needed molecules. So this is why the other way is we are going to use chemical reaction. All right. For example, if we use the general knowledge of chemistry, saying at some point we are going to need more hydrogen energy, say this is a needed target, then we try to look for all the molecules which have the hydrogen component. We try to think of ways to convert, to react those molecules and to produce hydrogen. So there you may think of, hey, how about I'm going to split water to produce hydrogen? How about I'm going to have natural gas, lots of natural gas. Maybe I can split natural gas to create more hydrogen. So those would be the through the reactions. And then before doing anything, we want to come back to thermal to understand that if I'm going to use water, say, as the reactant to produce hydrogen, what would be the desired temperature and the pressure condition, right? Of course, we want to minimize the energy import while receiving the quite nice yield over there. The other is, well, what would be the theoretical yield if we are willing to pay as much as needed for the energy? Then what would be the maximum yield using water as a reactant? So those analysis we have to run the thermal analysis to have those answers. So this is why we need to look at the reaction and how to set up the equilibrium calculations over there. So that is the first slide I want to quickly go over, especially remind you of the T-shirt equation over there. So now if we try to look at the general things about chemical reaction. So here I'm using the natural gas reaction. This is how I prepare my breakfast, I believe. So this is methane is burning, reacting with oxygen, will produce CO2 and water. And of course, we have other types of complicated reactions. So in general, if you look at those reactions, we should be able to group all those reactions into the following 4 groups. One is called a synthesis reaction. So A and B react will produce the molecule AB. The other is decomposition. We are going to have the AB split into 2 other new molecules. And then we are going to have the replacement and for double and single. So if we are looking at those reactions, then if you recall the calculation we did, then basically we can pick up any molecule over there and describe the change. So if we are going to look at methane, then we can describe the reaction by the change of methane in the number of moles. Because we understand that once we have the balanced chemical reaction, then the change is always proportional to their stoichiometry coefficients, those values, right? So this is 1, the stoichiometry for methane is 1, oxygen is 2, um, CO2 is 1, and water is 2. So that means if I'm going to burn, if I'm going to react 1 more of methane, then I need to have 2 more of oxygen. At the same time, when I finish the reaction, I'm going to produce 1 more of CO2 and 2 more of water. Although I don't know their state because I don't know the temperature and pressure, but if I also know the temperature and pressure is known, then I can also tell you what would be the thermodynamic state of water, whether it's in the liquid phase or vapor. So that's CO2, right? So this is the very general analysis. So we don't necessarily need to understand all those 4 components and their change as a function of the reaction. So this is our general feeling from chemistry. So over here, we want to think about how I'm going to come up with a new quantity and using that new quantity to describe the whole reaction and all those changes of the reactants and products. So before that, on this slide, I was simply reminding you that whenever you're having the reaction, all those would be of interest to us. The first is the mechanism. Uh, there we want to see how methane molecules will collide with each other, with methane itself, with oxygen, and when that collision will further lead to the chemical reaction. And along that collision or reaction path, what would be the energy barrier? And if the energy barrier is too high, how can we bring down the energy barrier by using catalyst? So those would be the mechanisms related for the reaction. And of course, we are also interested in the time-dependent quantity, say, is this a fast reaction or it's a very slow reaction, right? So this is related with the rate and the reaction kinetics. And for thermal, we shall be able to answer the equilibrium conversion. If I'm going to start with 1 mole of methane, 2 mole of oxygen, and I can tell after this chapter 14, if I'm going to have 500 Kelvin, 10 atm, then in the end, after the reaction, what would be the molar fraction of CO2, of water, of remaining methane and oxygen. So in that reactor, what would be their composition? So let's use Xi to express their composition. And if I'm going to manipulate the temperature and pressure, am I going to produce more CO2 or the reaction yield will actually decrease? So this is a question we try to answer by this chapter 14. Okay. So moving on, we want to look at in thermal, we are going to discuss all the following concepts over here in this lecture. One is the reaction stoichiometry. And the second is we want to understand that if the reaction comes to the equilibrium, what general equations we are going to set up and calculate in order to determine the equilibrium composition. And then, of course, one related other interesting question is, does that equilibrium change if I'm going to have a fixed temperature and pressure? If I now have more methane to start with, instead of 1 more, I have 10 more. Does that change in my equilibrium constant? And the other question is, temperature can be easily manipulated during the reaction. How do I know I need to increase the temperature or decrease the temperature in order to have a better yield? So this is why we need to set up the equilibrium constant and its related calculation in order to figure out the effect of temperature and molar fraction. The last thing is not necessarily we shall deal with the single reaction. We may have the other reaction to produce byproducts. So now if I have multiple reactions, how do I understand the need and try to manipulate the conditions so that I'm going to have the majority conversion to the desired products, not byproducts. So we should be able to answer all those questions after the 3 lectures altogether. So coming back to the reaction progress. So if we try to look at this general equation, general reaction over there, molecule A is reacting with B to produce C and D. And if we balance the reaction, then we always have those stoichiometry numbers, right? So here we try to use nu A, nu B, nu C, nu D to describe those numbers. And we understand that if this is the reactants, then this will be the negative value because we are consuming the reactants to produce the products as the reaction move forward. And those new values should be positive for the products. So if we look at this methane reaction, then the stoichiometry for methane is -1, -2, +1, and +2 for CO2 and water. So that is the first thing we need to identify the stoichiometry numbers and when they are positive or negative. So this secondly is when we are having the reaction progressing, then there shall be a change of the number of moles of everything, each reactant and each product. So in order to see that, then we need to come up with this equation. So here DNA is the change of species A during the reaction. Okay, we don't even need to define whether this is a positive change or negative change. Meaning if this is the reactants, then DNA shall be a negative value because we shall consume the reactants to produce reaction products, right? So as the reaction moves forward, then the number of moles of reactants shall decrease. So DNA itself should be a negative value if we are looking at a reactant. But at the same time, if we are looking at the corresponding stoichiometry value for that reactant, nu A is also a negative value. So over here, we are going to have altogether a positive value to describe the progress. Same story if we are looking at the product of D, we are going to produce the products. So DND shall be a positive value as the reaction goes on. And that new D shall be also a positive value. So overall, we are going to have a positive value over here. This is also overall a positive value, right? So now we have the ratio, meaning, well, there is some constant if we are looking at this one single reaction. And over here, we are going to define this ratio as a reaction coordinate. We use the name of coordinate because that is a good descriptor for us to see whether it's moving from 0, means no reaction at all. So that is at the very beginning of the reaction. And then in the end, we are going to have some value of that epsilon. And if we are going to have epsilon goes very close to 1, then this is a really perfect reaction because it's moving almost to the completion of the reactants. Generally speaking, then this epsilon shall be from 0 to 1 for most reactions. So you can see that we here define this reaction coordinate epsilon. And that is a very small change because we are looking at a small change. D means a small change of the components. So if we now have this very general descriptor for this single reaction, then we can describe all the components and their changes as a function of that ipsil, right? So this is why now if you move to the next equation, we are going to describe any reactants and products as a function of this d ipsil. So here dmi, the change of component I, is expressed by the corresponding stoichiometry number nu I multiplied by this reaction coordinate change d ipsil. Right? So this is the first equation. And that's also a very typical thermal discussion. We try to analyze the problem setup. We try to define some quantity, and then we try to move forward with the equation to see what would be the working equation we are going to have eventually. Okay, so now if I'm going to have the change, and that is a description for the change, a small change. And then, of course, we are not satisfied by looking at a very small change. We want to have the overall change. So in order to run the overall change, then mathematically, we know we need to run this integration, right? So now we start with this very general equation to look at the component I and its change. So over there, we say this is the initial. Initially, I'm going to have that many moles of component I. It could be 0 if this is a product. It could be some finite value, say 10 mole of methane if this is a reactant. Then I want to see at any time of my interest, what would be the number of moles of that component. So this is why we are running the integration from the initial to the final. Okay, the same type of discussion we've adopted many times in this class. So now if you run the integration, you quickly realize that those stoichiometry values shall be constants. If I know that specific reaction, those values are known to us, right? So the nu I shall be known to us if I have the reaction, the balanced reaction. So this is why you are going to run this integration. This is the initial. No reaction has happened. So the reaction progress, the reaction coordinate is 0. And then this is at any final value or at any final state of the reaction, we are going to have the genetic ipsil. Around the integration, this should be mi ni of the final minus ni of the initial. We usually use ni naught. That should be the constant of nu I multiplied by this ipsil. Okay, and then rearrange the initial, we shall have this term. So by understanding the process, we are moving to a pure mathematical description of this reaction. So over here, we need to know the reaction, the balanced reaction, so that we know the nu I values. And we also want to define the very general descriptor epsilon, so we are able to describe the progress. We also want to know initially what will be the mixture, how many reactants, how many products. It is not required that you start the reaction by having only the reactants. You could have a mixture of reactants and products, and then you just utilize the reaction to convert one into the other. Okay, so we have the forward reaction. We could also have the reversible reaction. Okay, So on this slide, there are two equations shall have our attention, but eventually now we know how to describe the change of each component over there. So you see that we are interested in the overall, and of course we want to keep an eye on, well, what is the overall number of moles, right? So I hope that you see that once we define the general expression of Mi, then we shall move on and we try to look at, let's run the summation of Mi. Let's try to look at the total number of moles for the system. So this is exactly what we will do on the next slide. Over here, this is the expression we just derived. Then if we are going to run the summation to identify all the species in this reactor, then we are having, this would be the summation of the initial. And if you are going to run the summation over here, you can see that this epsilon is a constant for the reaction. So if you are going to run the summation, then you are summing over the new I value. So this is how we are going to have let's try to put down the methane, oxygen, CO2, and water. Going to have two. We are going to have two over there, right? So we said the stoichiometry would be -1, -2, +1, +2. So those would be their corresponding stoichiometry values, and the overall would be, right? Pay attention to the sign. So this would be, this would be 0 for this specific reaction. So this is how we are going to have the overall number of moles, and we're able to express this by the overall initial. This is the reaction coordinate. This is the overall stoichiometry value. Okay, if we know each component, if we know the overall, then naturally we shall receive the molar fraction at any moment of the reaction, right? So this is simply the ratio between Ni and N. And then you just plug in. So Ni is Ni naught. There is a type over there. This should be the new I. Okay. And then for the denominator, we are going to have N naught of the total. This is the new of the total. So that two equations you may want to take a look at to see whether they are making sense or not. Okay, so far, are we happy with all those discussions?
Well enough. Best I can.
Good to know. So now let's move forward to see, here I have this one example, ammonia. We are going to burn ammonia with oxygen, unfortunately produce NO and water. So the equation is balanced. And then we were told that initially we have 2 more of ammonia, 5 more of oxygen, and we need to look for the molar fraction of the reacting species. Reacting species meaning we need to figure out the Y for ammonia and the Y for oxygen. We're using X and Y depending on the understanding of the thermal state. So here we are dealing with the gas, so we tend to use Y. If we are dealing with the liquid reaction, then we tend to use Xi to be consistent with the previous descriptions. So over there, first of all, we want to have the Ni expression and N of the total, right? So that we know Ni will be Ni naught plus nu I reaction coordinate. And total would be N total of the initial plus nu multiplied by the reaction coordinate. So over here, we need to understand that this is nu. So this is why we try to calculate the summation of those stoichiometry values. So that's -4 for ammonia, -5 for oxygen, +6 for NO and water. So that is 1, and then initially we are going to have that number of moles coming from ammonia and oxygen. So once we know that, we shall be able to just go ahead and use that two equations. So this is the N of the initial, this is overall. Pay attention to the two different stoichiometry values. So that is 1, but for ammonia, that's -4. Similarly, we are going to apply that equation to oxygen. So we have the initial oxygen, we are going to have this. And if I want to have this expression for water, what's water? Well, water is N water, right? Initial plus the stoichiometry value for water multiplied by reaction coordinate. And that is N of the total at initial. This is nu and epsilon. So if for water, the denominator will be still the same. We have no initial water molecules, so this should be 0. And then this is a +6. So the final answer is, right? That is for water. I hope that's straightforward. Is it? Okay. So now let's try to look at more reactions. All right. So using the previous example, we can easily come up with, well, this is to NO and water. And I could easily manipulate NO2 and water, right? So that is the two reactions that we typically have when burning the ammonia. So what's going on if I have two reactions? Then number one is we need to recognize that when we talk about the, and by the way, I don't have the two reactions balanced. So we need to balance the two reactions before doing anything. And I am just too lazy to do that now. So over here, we need to recognize the most important concept. When we are talking about the reaction coordinate, each reaction shall have its own reaction coordinate. So over there, we'd better understand this is the reaction coordinate 1. This is the reaction coordinate of 2. Okay. This is the first. And then when you look at the two reactions separately, you need to also identify that I'm going to set up the calculation, say if this is for ammonia, then I need to identify this first equation is talking about the reaction 1 over there, so that I can understand this is the reaction 1 total plus this is also the reaction 1 of the overall stoichiometry values multiplied by the corresponding reaction coordinate 1. And over here, I'm going to have the ammonia initial out of reaction 1, right? Then over there, I'm going to have the ammonia stoichiometry value, but also for the reaction 1 multiplied by the corresponding stoichiometry value. Similarly, you are going to have the ammonia number of moles involved in that reaction 2. Then over there, I'm going to have, now I need to identify this is about the reaction 2, and I need to identify this is the overall stoichiometry value for reaction 2. And then I'm going to have initial ammonia assigned for the reaction 2. I'm going to have ammonia stoichiometry value for reaction 2 multiply. All right. You may have the question that how do I know the distribution? If I start with 1 mole, if I start of 1 mole ammonia, let's say 5 mole of O2, how do I know the distribution of the ammonia? Well, we don't know that, but we are going to know that this N ammonia initial of 1 plus N ammonia initial of 2 should be 1, right? That we know. And we also know, if I know this is 1 mole of ammonia and 5 mole of water, no, oxygen, then I know that the initial of 1 plus initial of 2 should be 6. Okay, so this is why we need to set up multiple equations in order to solve for epsilon 1 and epsilon 2. This we don't know for sure, that we don't know for sure, but we are going to have the 2 equations to help. Okay. So those would be the ways when you have multiple reactions, how you are going to deal with that. So now let's try to look at the equations. We said if I'm going to have the reaction coordinate for each reaction, then pay attention over here. We need to identify the reaction coordinate for all those equations, and you need to run the calculations individually for each of them, for all the components. So ammonia and oxygen and water will be a little bit more complicated, but NO and NO2, we just utilize one reaction coordinate. Okay. Then nothing special, we just need to add up all those components like we have in this equation. So sometimes the equations themselves, they don't tell too much. So this is why we'd better look at this example. Very similar to the example we just described, right? So now we are going to have C2, and we try to have the reaction with oxygen, but then unfortunately we are going to have this side reaction over there. And then if we know that we are going to have 2 more of C2, 3 more of O2, oxygen, then we need to find the expression for both. This is for Y, C2, and Y of oxygen. Okay, I believe this is one example from the textbook. So I'm going to stop here and ask you to read the textbook and figure it out. Okay, I can tell you that in the final exam, there will be reactions involving two reactions, no more, but it's definitely not one single reaction type of calculation. So you need to be comfortable with the initial step to identify what would be the corresponding yi or xi values out of the two reaction system. So pay attention to this example over there and try to make sure you are able to go from the beginning till the correct expression. Okay, so that's just the stoichiometry values and the reaction coordinate and how we are going to come up with the expression. But then you may wonder why we want to express all those expressions. Look at the change of each component as the reaction is making progress. Well, in order to do that, we first of all we need to get the working equation for our problem. So in order to do that, we need to recall when we talk about the Gibbs energy change, we were talking about G is the descriptor for both VLE and reactions, right? So the Gibbs energy is a descriptor for the two most interesting processes over here in thermodynamics. So this is a previous slide where we know that the Gibbs energy shall have the minimum or shall have the partial derivative goes zero when you reach the equilibrium. So that is the condition we are going to utilize. If I know the temperature and pressure, then I just need to monitor the change of the Gibbs energy. When the reaction is making progress, when we are going to have the redistribution of those molecules, then the total Gibbs energy of the system is changing. And it will stop changing when I reach the equilibrium. Okay. And at that equilibrium, this dg value shall be zero. So this is the mathematical point we are going to utilize. Okay. So here we need to express G, but what is the total Gibbs energy of the system? That should be easier to us because we start with the four energy equations long time ago. And then when we talk about the mixture, right? So at the very beginning, we say G is the function of Tp, and then you are going to have the fourth derivative of dg is what? I cannot memorize. Vdp sdt, something like that, right? And then we say, well, I'm going to describe the mixture. The reacting system, the VLE system, they are all talking about mixtures. So this is why we are going to extend G as a function of Tp and X coming out of multiple components. And then we have this modified dg is blah, blah, blah over there. And this is how we notice I need to define the chemical potential. Okay. So go back and double check some slides to see how we are going to come up with the Gibbs energy equation for a mixture. So the answer I'm going to copy, well, this is basically the mathematical expression to show you that if you try to plot the total Gibbs energy and its change as a function of the reaction. So this is a reaction coordinate, this is 0, this is 1, then this is the initial. And we call this as a final because this is the equilibrium. And once the reaction reaches its equilibrium, it will stop, no longer changing over there. So this is why mathematically we are interested in identifying this one. Equilibrium reaction coordinate. So if we go back to the expressions, that is the expression. Okay. It's indeed VdP SDT. And we try to use n multiplied by g to make sure we understand this is the total Gibbs energy. If we are going to carry out the discussion using one more base, then of course we can say dg is VdP SDT and mu I dxi, so on. Right? So you see that the whole morning, the past 45 minutes, so on, we were talking about for those reaction coordinates. Simply, we want to receive this equation, right? This is coming out of the definition. We define dmi over corresponding stoichiometry nu I is defined as d epsilon. That is the change of the reaction coordinate. And I hope you feel excited that now we are going to plug in, right? Nothing special, really, really nothing special. So we are the master of chemical potential, yes? Now we need to look at the DMI. DMI is nothing special. DMI is my stoichiometry, which is a known value, for the reaction, right? Multiplied by, that is something we need to figure out. So anyway, now let's try to simply replace DMI. Now you are going to have the Gibbs energy change of the system is VdP minus SDT. We have this summation over multiple components. So now we still have the mu I. DMI is replaced by nu I d epsilon, right? So here we are using the very general Gibbs energy for the mixture. Now we try to apply that for the reacting mixtures. So over there you can see that if the temperature and pressure is known, meaning dP and dt would be 0, then at the reaction equilibrium we shall have so fixed T and P, we are going to have dP is 0, dt is 0. So at the equilibrium, we shall receive dg over the reaction coordinate, which is coming out of the previous plot. This is the minimal, so that we are going to have the first order derivative dg over d epsilon shall be 0 at this point, which is equilibrium. So this is why without doing anything, we have not done anything yet. We just reorganize this d epsilon to the left-hand side. Then we know that at equilibrium, we shall satisfy the summation of chemical potential nu I shall be 0. Okay. And now when you look at this, and I hope you feel really happy that nothing special, right? So moving out of the general VLE to the reacting system, we're not changing anything. We are still doing the chemical potential calculation, but we just need to modify the equation so that we are going to have the chemical potential multiply by its corresponding stoichiometry coefficient. And then for that reacting system, the overall, the summation of that expression shall be 0. Okay. Are we still very happy so far?
Sure.
Sure. Thank you, Connor. Others are
You're welcome.
asleep, I believe. So now moving forward, well, we are spending the whole morning to have this equation. And the following will be our regular business. Now let's try to look at the chemical potential calculation. Okay. So the following slides were coming out of the previous session. So first of all, we need to look at this mu I, right? Then probably replacing the chemical potential calculation by the fugacity calculation. And if that is a mixture, let's try to put it add. And then when we are going to replace the chemical potential calculation by fugacity calculation, then we need to understand that this fugacity is coming out of the comparison with ideal gas, which is RT d log pi for the ideal gas. And then we have the definition of fugacity d mu I is RT d log Fi. This is how we define fugacity. This is for ideal gas, this is for anything. Anything. Okay. And over there, well, we are not looking at the d mu I, we are looking at the mu I itself. So we have to solve for mu I, where we have to run the integration. So now if you are moving from d mu I of R RT d log Fi, we run the integration from the initial to the final. This is RT. And of course, oh no, that's wrong. Integration. This is initial. This is final. And then keep it in mind, this is at fixed. So R and T, they are simply constants over there. So now we need to be wise in picking up the initial condition, right? So for the initial, the default choice is standard state, right? Sometimes from there, we say, if we are lucky, we try to pick up the extremely low pressure, like we did for the steam table calculations. If we are lucky, we try to use very low pressure. I know that my iPad is complaining. For the low pressure, then we can have what? For the gas phase, it's ideal gas. For the vapor, no, for the liquid. Maybe we are lucky to correlate something of the saturation pressure because it's the low pressure region. So for the fugacity calculation, we can correlate to the saturation pressure. So that is one sort of thought. The other is, well, based on whatever data you have. So there's a typical temperature out of our appendix, out of the previous measurement. So this is why this 298 Kelvin, that's not a magic temperature. It is just a temperature we the people have done lots of measurements. So we have lots of data over there. Right? So if you are using the textbook appendix to run the calculation, that is always a convenient choice. Okay, so if you recall those discussions we had, then I think on the left-hand side of the slides, I hope I'm not going to scare you by the two equations. Okay, I purposely use this one so that you somehow see there is a connection. There is a connection between chemical potential to the Gibbs energy. It's partial molar Gibbs energy, right? So anyway, if I'm going to write down this, and that is just a reference value. This is just a reference. It's coming out of the fourth derivative of the chemical potential, and I just utilize that for two different conditions. So this is the mixture, and that is for the pure component at that standard state. Okay, so that is for the standard state. And over there, you can see that this is mu I, or if you want, you can express this is mu I naught. Then this would be RT. This would be exactly the same expression I have over there. And that is the equation we've utilized multiple times in the past lectures. So here I have this hat out of the mixture. I probably have to save the notes, otherwise it might be too many. So iPad cannot carry on. And that is for the standard. Okay. Let me save the notes to see if it's improving. All right. So what do we do? Well, we have this top equation, and that's for any reacting system of mixtures. Then we know how to express the chemical potential by the fugacity with the help of a reference state. Then, of course, we are going to replace mu I by the last equation on this slide. So if I move on, you can see that I'm doing nothing special but replacing this was mu I, and I'm replacing mu I by the chemical potential definition, or the connection between chemical potential and fugacity. Okay. So I hope this equation is not surprising at all. And then we just reorganize. So I'm going to redistribute and reorganize. Now I'm going to have the two terms over there, right? And then I'm going to further reorganize this. I'm going to put the new I as the exponential term. So I'm going to put that into the log equation. Now I have new I over there. The last thing I can do is, well, let's try to reorganize the terms. So I'm going to have this, the summation of the log I'm going to manipulate. So that will be a product of this. So I want to make sure we are happy in switching from the summation term to the product term. So that is basically if you are going to have log f1 plus log f2 plus log f3, that is the summation of log fi. Let's say I is 1 to 3, right? So that would be the same as you are running. Let's say this is the same as log the product of y equals 1 to 3 for this specific term fi, which is log fi, no, f1, f2, and f3. Okay, so pay attention to this switch over there. So this is how we are changing from the summation term. If we are having the log operation, then we are able to switch the order and convert that into a product. This is just the example. Okay, so now we switch the operation, and then we are going to reorganize. So that is pay attention to the minus. We move the first term to the right hand side of the equation. Then this is the equation we have over here. So I hope looking at the equation, at least we know that the temperature is known because that's coming out of the fixed Tp. So we know the temperature, we know the gas constant. If I have the reaction, I know the stoichiometry nu I values. And if I know the reactants and products and I have the appendix, then those Gi naught, those values I shall also have, right? So that means if I have the reaction, the balanced reaction, and I have the appendix, I know the temperature, then I know the right-hand side term. Okay. How about the left-hand side? That's our favorite fugacity calculation. So far, I have no idea. If we run out of ideas, let's just name a new parameter. So this is why we are going to call the product as capital K, which is the reaction constant. Okay. So now moving forward, I hope you're not very surprising. So this is still the equation we have over here. Still pay attention to the negative sign over there. And we are going to define, this is K, capital K. Okay. At the same time, we are going to pick up some other summation value. For example, this one, if I know, let's still use mass in the reaction over there. This is H4 producing CO2, producing 2 more of water. Then I know at the standard, let's say at standard state, I know this one, CO2. I also know this for water. Then you can see that I can quickly know what would be the delta G of this standard state, which is the summation of nu I of Gi naught. Oh, I have the equation over here. Okay. Ask yourself, where do you get those values? Remember when we are dealing with chapter 4, I believe, we're doing lots of formation, reaction, enthalpy calculations, right?
Can you look them up in a table or?
Yeah, that's where I'm trying to lead you guys to. So that is from the appendix. Okay. So in our textbook, we have a specific standard state, which is 298 Kelvin. That is our standard state. And we have lots of data measured at that temperature. So in short, this value is known to us if I know the equation. So by hiding the fugacity, now we are receiving this very pleasant equation, right? This is simply log k is minus delta G of the standard over RT. Always pay attention to this one. Okay. And we will leave the most difficult part to the last. Okay. So far, if you look at this, and I hope that from Pecan or from general chemistry, you may vaguely recall we had some equation to correlate the heat of formation, heat of reaction, the temperature with respect to the reaction equilibrium, this capital K. And this is how we actually receive the equation from scratch. All right. I know that you've almost forgot everything after the Thanksgiving holiday. So this is why we try to recall the discussion of the four energy equations, the fugacity and chemical potential. So hopefully we will pick up those nice memories. Okay. So now move on. Let's try to see what's left for us for the equilibrium constant K. So now if we have log K is minus delta G naught over RT, then of course if you want to have the K value, then this is the exponential term, right? So this is just changing from log to exponential, nothing special, and then we just have this delta G naught as the combination of each reactant and product. I do want to emphasize that typically K is a function of temperature. As we can easily see that K is, once I know the reaction, then this term shall be available to us at a specific temperature. But while you are going to change the temperature, then you are going to manipulate the K value. So the equilibrium constant is a function of temperature. We have to recognize that. So I also have one slide just in case you want to review about the standard state. I'll leave this to you to read how we typically define IUPAC standard state and what would be the convenient standard state, which is okay. So it's also the standard state. It's just a typical standard state by having those available data. So this is still the relaxing slide, nothing special. K is a function of temperature, and we need to have the standard Gibbs free energy change out of the reaction. Okay, we will repeat it from the previous slide, and you may recall this is the type of plot we are reading, looking at the slope, what we are going to have, and look at the specific temperature, what would be the reaction constant we are going to have. So this is typically plotted by log K over 1 over T. So that shall be a straight line. that's going to correlate. This is log k. If you over 1 over t, then this slope should be negative delta G naught over R. Okay. So this is why if you are going to have the exothermic or endothermic reaction, then you would have this as a positive slope, or you are going to have this as a negative slope. Okay. Everything is possible. So I'm going to stop here, but I want to leave this slide and I'll come back and hopefully someone will help us to understand how do I receive this equation. Okay, so this is the last thing I want to mention, and I hope you will come up with understanding and help me to address how do I move now from delta G to delta H. Of course, this is the same standard state calculation. So if we can figure out that, then I think we're able to connect chapter. This is chapter 14 with chapter 4.
Okay, I think we can do that. Anahita, you can get there, right?
All right.
Oh, you're a champion. You're a champion.
Not at the moment.
Okay, that's all I have for you guys, and we'll come back on Thursday for more exciting discussions.
Thank you.
Word.
Professor,
Thank you. See you Thursday.
Sure. What's the question?
can